So we move on to the next module, which is formal specification and verification of programs. So we have seen syntax semantics for both propositional logic and first order logic, as well as some examples of decision procedures, right, for validity and satisfiability. So all of these things that we have seen so far, right, they form the engine, right, for deductive verification of programs. So now we will see how to reduce this verification problem to the satisfiability problem in first order logic. So this is a very simple sort of diagram, right, which illustrates how deductive verification works, right. So the idea is quite simple, right. So given a program and the specification, right, so as I had mentioned at the very beginning, right, of this course, that a program by itself, right, does not have a meaning, right, since that you don't know what that program is written for, right. So you also need a specification, right, which is the correctness property that you want to check for a given program, right. So there is this tool called deductive verifier, right, and we will see in this module what this deductive verifier looks like, right, which takes as input this program and its specification, right, what you want to check, right, or what is the correctness of the program, right, and then it constructs this FOL formula, right, which is then passed on to an SMT solver, right, or a theorem prover, right, and then this theorem prover will say either this formula is satisfiable or it is not satisfiable, based on which the verifier will conclude, right, that either the program is correct or there is a counterexample, right, or there is a bug in the program according to the specification. Okay. So we have seen, right, brief glimpses, right, of what this particular block, right, SMT solver or theorem prover looks like, right, and we have also seen syntax and semantics of FOL formula, right. Deductive verifier we are going to see in this module, right. We know, all of us know what a program is, right. What about specification, right? So there are various ways in which you can write specifications. Okay, the specification is the correctness condition, right, that you are checking. So the programmer has to give the specification as input to the deductive verifier, right. So you can write the specification in various forms. So it can be given in the form of assertions, right, which are essentially properties that you want to check, right, regarding the state of the program, right. Also preconditions, postconditions, invariants, and so on. So we are going to look at all of these different forms of specification, right, for writing correctness of programs. So in order to illustrate, right, the specification and the verification process, we are going to use a very small synthetic programming language, right, which is called IMP, right. So this is a very small imperative programming language. It's not a real world language, right. So in practically it is not it's not a correct way, right, to directly jump into a real world programming language like C, C++, or Java, right, which has lots of features, right, and which may hinder our understanding of how things work, right. So we will first start off with a very small imperative programming language, right, which has very minimal features, and then gradually we will build on the features, right, of the programming language. Okay. So let us first define some necessary notation, right, in order to write programs in this IMP programming language, right. So we will, at the very beginning, right, we will start off with a set of program variables, right. So in the IMP programming language, we are not going to allow program or rather variable declarations, right. So at the very beginning, right, we will say what are the set of program variables, and then we won't actually declare all the program variables, right, as they appear in the program. So you can just directly say what are the program variables and then directly use them in the program, right. So let's say V is the set of program variables. Okay. Now using this program variables, right, you will construct different kinds of programming statements, right. So we are going to use some notation here, right. So we will define these two notations, expv and phi-v, right. So what does expv mean? So expv is the set of linear expressions, right, linear expressions over the program variables v, right? And phi-v are the set of linear formula over the program variables v. So again, right, to tie this with what we have seen so far, right, so we have seen this theory of integers, right, or the theory of real numbers, right, the theory of rationals. So LIA is linear integer arithmetic, which is the theory of integers, and LRA is the theory of rationals, right, or the theory of real numbers, right. So this expv, right, this the components, right, or the elements of expv are all terms, right, in LRA or LIA, right. So term, again, right, term meaning that so this is a term on first order logic, right. So what this means is So it is essentially just an application of a function, okay. So a function which is in LRA or in LIA, right. So remember that each of these theories, right, define functions. So for example, the theory of integers, right, defines functions like plus, minus, right, or multiplication by a constant, right. So this we saw as this n dot, right. Similarly, the theory of real numbers has its own functions, right. So any terms that you can construct by applying these functions, right, these are all part of this set called EXPV, right. So in fact, they will be the set of linear expressions, okay. Phi v are formulas in LRA or LIA, right. So again, formula, when we say formula, this is first order logic formula, right. So this is essentially obtained by applying logical connectives, right, on predicates, right. So again, each of these theories defines predicates, right. So for example, LIA has this equal to, less than, right, greater than, less than or equal to, greater than or equal to, right. These are the predicates that are defined by LIA, right. And now using these predicates, you can apply these predicates on terms to generate formula. You can also use logical connectives, right, in order to generate formula. So this phi v is the set of linear formulas, right, over V. So let's look at some examples, right. So for example, 3x plus 2y, right. So this is a formula, this is a term, right, in linear integer arithmetic, right. So it's using this function plus, right, and it's also using the multiplication by constant, right, which is this 3 dot and 2 dot, right. So this is a term in the theory of integers, right, in linear integer arithmetic, right, and therefore this belongs to this particular set, right, which is exp of x comma y. So it's using these two variables, right, x and y, which are program variables, right. So over the program variables, you can construct arbitrary linear expressions, right, using the functions that are present in the theory of integers, okay. And all of those linear expressions will be collected in this set exp x comma y, right. Similarly, this phi is formula, right, is the set of all formulas, right. So here, for example, I am constructing a formula over 4 variables, right, x, y, z and w. And why is this a formula? So it's using logical connective, right. So it's using this logical connective and it's also using these predicates, right, less than or equal to and equal to. So both less than or equal to and equal to, these are predicates, these are part of the signature of the theory of integers, right. And then once I construct these two predicates, right, I can then combine them using a logical connective, which in this case is AND, right. So therefore phi v will be the set of all linear formulas over V. So now let's see why we have defined this EXPV and phi v, right. So here is the grammar for the IMP programming language, right. So the grammar for the IMP programming language, right, which we denote by this particular grammar symbol C, right. So so it can either be this base statements, right. So there are 2 base statements, right. In fact, there are 4 base statements, right. So the first 2 base statements are assignment statements, right. So you can write x colon equal to exp and x colon equal to havoc. So both of these are assignment statements, right. So they are used to assign a value to a variable, right. So here x is a program variable, right, and we use this colon equal to notation for assignment. Now what is this exp and havoc? So exp in fact is a linear expression, right. So it's any expression, right, it's any term in linear integer arithmetic, right. So therefore exp belongs to exp of V, right. So which means that you can essentially construct any linear expression out of program variables, and then you can use that linear expression as the right hand side of an assignment statement, right. Similarly, okay, let's look at what is havoc. So havoc is how we simulate assigning random values, right. So when you say x equal to havoc, you are essentially assigning some random value to x, right. So you don't have any control over what value will be assigned to x. So we will see exactly where this x equal to havoc will play a role, right, later on, right, in particular while verification, right, while doing verification. Okay. So next we have this assume f and assert f, right. So here what is this f? So both assume f and assert f, right, they are both the base statements, right, and f is a formula, right. So it's a formula in the theory of integers, right. So f belongs to phi of V, right. So which means that you can essentially construct any formula, right, over the program variables, right, and then either assume or assert that formula. So again, what does it exactly mean, right, when we say assume f or assert f we will see later on. Okay, but for now let's just focus on the syntax. The semantics will come later. Okay. So once you have all these base statements, then you can combine these base statements, right, to form compound statements. So what are the compound statements? So I have skip, right, which does nothing, right. So skip is something like no op. Right. Then I have sequential composition, right, which is C semicolon C, right, and then if then else and while loop, right. So if f then C else C, and then while f do C. Notice again this f is present here, right. So this f again, right, is a formula, right, in the formula over the program variables, right. So I can, in general, right, you construct any formula and use that as a conditional, right, in both the if then else statement as well as the while loop. Okay. So this is the syntax of our IMP programming language, right. So as you can see, right, it has the very base features, right, that you may expect out of any imperative language, right. So it has assignments, right, it has sequential composition, and it has your if then else and while loops. Okay. And in addition there are a few special features, right. So there is this havoc, assume and assert. So let's see what they do. Okay. So here is an example of a program in the IMP programming language, right. So this one has 3 statements, right, which are all sort of composed together through sequential composition, right. So there is sequential composition here, here and here. Okay. So I am using the assume statement here, right. So note that assume, right, to assume you can pass a formula. So this is a formula that you have constructed, right. This is in the theory of integers, right, because it's using equal to and greater than or equal to as well as logical connective and, right, and I and n are program variables. So you can see that I don't have to declare program variables, right. So what is this simple program doing? So it's initially assuming that I is equal to 0 and n is greater than or equal to 0, and then there is this while loop, right, and again notice that the conditional that is used inside the while loop, this is a formula, right, over the program variables I and n. So while I is less than n, do I colon equal to I plus 1, right, and then finally we are asserting that I is equal to n, again a formula. Okay. So often this assume and assert, right, so we will typically see that assumes will come at the beginning of the program, right, although this is not a syntactic restriction, right, but this is a more of a convention, right, that all assumes will appear at the beginning of a program. So they are what are called preconditions, right. So these are your sort of starting assumptions, right. So you are starting the program with these assumptions, right, while the asserts will appear at the end of the program, right. So they are what are known as post conditions, right. So this is your correctness criteria, right. So this is what you actually want, right. So what you want to say is, if you start this program in a state right, where the variable I has the value 0 and the variable n has the value greater than or equal to 0, right, then this simple loop, right, all it will do is it will essentially count, right, I, right, so it will increment I up to n, right, and when this loop terminates, then the value of I will be equal to n, right. So and that is what you are trying to assert, okay, using the post condition. So as we have already seen, right, to assume and assert as well as to while, the conditionals that are given are all formulas, right, in LIA, whose free variables are program variables. So these formulas do have free variables, right, they don't have any quantification, which means that you can have free variables, but all the free variables should be program variables. Another way of writing a precondition and post condition is to use this curly bracket notation, right. So if you don't want to use assume and assert, right, you can just have this curly brackets, right, at the beginning and at the end of the program, right. So again this means that this is the precondition and this is the post condition, and this is how we will typically write a specification, right. So this is one form of specifying the correctness, right, of a program, right. So the specification is different from the implementation, right. So the program is the implementation, right. The specification is what we expect out of the program, right, what is the correctness condition, and here it is specified in the form of a precondition and a post condition. So in order to specify the precondition and the post condition, we will use this curly braces. So here is a slightly more complex example, right. So suppose you want to write a program which does linear search, right. So linear search meaning that you have an array, right, and some lower limit and upper limit and some element that you want to search, right. So you want to find out whether or not this element E, whether or not it is present in the array, right. So this array, right, again we have not really explicitly said, right, that we will allow arrays in the IMP programming language, right? But in general, right, if any theory that you have seen, right, we can allow formulas, right, or expressions over that theory. So we have seen the theory of arrays, right, which allows array write and array read functions and so on, right? So therefore we will allow the arrays, right, to be, or arrays to be present in the IMP programs. Okay. So this linear search program, it takes as input an array A as well as limits L and U and some element to be searched, which is E, and it outputs true if the element is present and false otherwise. So this is quite a simple program, right? So it just does a linear traversal, right? So it just traverses the array beginning from I equal to L, right? And it uses this present variable, right, which is initially assigned as false, right? And then while I is less than or equal to U and present is false, you just iterate through the array elements, right, one by one. So if AI is E, then you have found the element, so therefore you say you set present to true, right? Otherwise you just increment I, right? And this while loop will exit when the entire scan, when the region of the array, right, between L and U has been scanned, right, or if the element has been found. Okay. So how would you write the specification, right, of this particular program? Okay. What is it that you expect out of this program, right? What is the correctness condition? So you expect that if you begin this program, right, in a state where, let's say, you have some arbitrary array A, right, and some arbitrary limits L and U, right, as well as some arbitrary value E, right, you expect first of all that this L and U, right, this should be within the bounds of the array, right? So you don't want to go outside the bounds of the array. So this array, right, typically will start at the location 0, right, and it will have, right, some maximum length, right? So you want this L and U to be within the array bounds, right? And this is a precondition, right? So you can specify this as a precondition, right? Which means you can say that I am only interested in values of L, U and the array A, right, where L and U are within the bounds of the array A. So what is the post condition now? So the post condition, right, is based on this present variable, right? So you want to say that this present variable is true if and only if this particular element E is present in the array, right? So if the element E is not present in the array, then you want this present variable to be false. So this is what we want to specify. Let's see how we can specify this, right? So now in order to specify this, you have to write down a precondition, right, and a post condition, right? And both of these need to be formulas, right? They need to be formulas in the theory of integers, right, or in the theory of arrays in this case. So we want to write assume and asserts, right? So we want to write a precondition in the form of an assume, post condition in the form of an assert. So here is what the precondition can look like, right? So we want to say that L has to be, or L and U have to be within the bounds of the array. So you can say L has to be greater than or equal to 0 and U has to be less than or equal to mod A, right? So here this mod A you can assume to be some constant, right, which is supposed to denote the size of the array A, right? And again, this is using this less than or equal to and greater than or equal to, right, or symbols, right, which are both in the theory of integers. So what about the post condition? So the post condition has to say something about this present variable, right, and in particular it has to say, right, when this present variable should be true and when should it be false. So here is one way in which you can write the post condition, right? So you can say that present, right, if and only if, right, or by implication, L is less than or equal to I is less than or equal to U and AI is equal to E, right? So A read at the index I is equal to E. So what this means is that if, right, at the end of the program, right, so when you finished executing the program, if the present variable is true, then that can happen if and only if the value of the variable I is between L and U, and not only that, but the value of the array A at index I is equal to the element E. So you should notice that this particular formula, right, this is a formula, right, it's a formula in the combined theory, right, it's a formula in the theory of arrays and in the theory of integers, and moreover this formula has free variables, right? So present L, I, U, A, E, right, these are all variables, these are all program variables, right? These are all free in the formula, right? And what we are essentially saying, right, using this formula is we are trying to express a set of program states, right? We are trying to express the values of the program variables, right, at the end of the execution of this program, right? So we are trying to say that when you reach the end of the execution of the program, the values of all these program variables, right, they must obey this particular formula, right. So the values of present, L, I, U and A, right, they must obey this particular formula. Okay. So in fact, right, if present is true, then in fact it is the case, right, that I will be between L and U, right, and A of I, or rather A, the array A indexed at the particular location I will be equal to the element E. Okay. So but is this correct, right? So we know that if the element is present, right, then in fact it is the case, right, that that the present variable will be true, right, and if the element is not present, right, so in which case this I, right, will not be between L and U, right, because this, when this loop terminates and the element is not present, right, then the value of I will be greater than U, right, and in fact therefore since I is greater than U, therefore the present variable will be false, right. So you might think that, okay, this seems like a correct specification, right, but what I am going to demonstrate now is that this specification is not correct, right, it is not precise. This is because the reason why this is not precise is because it will allow buggy programs, right. So it will allow a buggy program, right. So now I will demonstrate that there is a buggy program which will obey this particular specification, but it is not serving our purpose, right. So it is not doing linear search. So let's look at this buggy program now. So let's look at this very simple program. Okay, so I have not changed the precondition, the postcondition, right. So I have not changed the specification, all I have changed is the program. So what does this program do? It's quite simple, right. It first assigns I to L, right. It just says present is equal to false, and then it says I is equal to I minus 1. So now, right, you can see that this program also satisfies this particular specification, right. So in fact it satisfies because present is always false, right, and I, the value of I is not between L and U, right. So in fact since we are assigning I equal to I minus 1, I is actually L minus 1, right. So this program also satisfies the specification, okay, but this program is not even traversing, right, it's not even looking at the array, right. So that's why this specification is very weak, right. So it's what we call a weak specification. So it is allowing buggy programs, right, to go through, right. It's not exactly expressing, right, the programmer's intuition, right. It's not expressing the programmer's requirement, right, which is that this present variable, it should be false only if there is no element that is present, or rather only if this array, this particular element E is not present at any index I between L and U. So that is what we want to express, right. So we want to express that this present variable should be true if there is some index between L and U, right, such that the value of the array at that index is E, and if there is no such index, then we want the present variable to be false, and here is that specification, right. So here I have not changed the preconditions. The precondition is the same as what it was earlier, but the post condition has changed, right. So now I am introducing this existential here, right. So I am saying that this present variable is true if and only if, right, this is by implication, there exists some x, right, such that that x is between L and U, and A accessed at that index x is equal to E, right. So now if you take this specification, right, this specification and the program on the previous slide, this program does not satisfy this new specification, right, because since it is not even looking at the array, right, so therefore it will not satisfy the specification, right. So it just says present equal to false, but it is possible that the element E may be present inside the array, right, while this program, right, this is the program that we originally had, right, which we feel is correct, will satisfy the specification, okay. So what this kind of reveals is that you have to be very careful while writing specifications, right. So the specification should accurately encode, right, the programmer's intent, right, the reason for writing a particular program, right? So in this case the reason is that we want to find out whether or not the element E is present in that particular segment of the array, right? So this is also demonstrating the expressiveness of first order logic, right. So in fact we had to use this existential quantifier here, right, in order to accurately express our intention, right, in order to accurately express the correctness criteria for this linear search algorithm.